Hello students, today we will see the part 2 of the solutions theory. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at SATHEE@itk.ac.in and we shall remove the same. In this lecture, our objective would be to see the Henry's law and the Rawls law. We will start from looking at what is solubility. Then we will see some examples. Okay. And lastly, we will cover some in-text questions. What do you mean by solubility? So solubility is something which defines the maximum amount that can be dissolved in a specified amount of solvent. So it defines the solute's maximum amount that can be dissolved in a solvent in a specified temperature. So you can't change the temperature while defining solubility. Now, the solubility depends upon the solute and the solvent both. Means what is their nature? Are they polar? Do they have the ability to do the hydrogen bonding within themselves? All of this factor contributes towards the solubility factor. And regarding the external factor, it depends upon temperature and pressure both. We will study about the temperature and pressure one by one. Then first thing that I mentioned about the solubility factor was the nature of the solute and solvent. Here in this example, how you can decide the solubility from the nature of the solute and solvent. So if I talk about the polar solutes, then you know it, then like dissolves like. So if polar solute is there, that means it will be dissolved in polar solvent. Whereas the non-polar solutes are dissolved in non-polar solvents. Example, sodium chloride, which is a polar one, as it is an ionic compound, it will dissolve in water, as well as the sugar also gets dissolved in water. Whereas the non-polar compound like naphthalene, which is a bifused ring of benzene, and anthracene, which is a trifused ring of benzene, they are very less polar and are not soluble in water, or their solubility is very, very less. Whereas, if you try to dissolve these two non-polar solutes into benzene, then they are easily dissolved. At the other hand, your sodium chloride will not go into this non-polar solvent like benzene. I hope you are getting the point on how the nature of solute and solvent are important. So in general, I would say that a solute dissolves in a solvent if the intermolecular interaction are similar in the two. So in polar type of solute or polar type of solvent, the intermolecular interaction is basically dipole-dipole interaction. Now, in non-polar solvent, the main interaction is the van der Waals interaction. So, the point here is that if the interaction that is present in solute and solvent are same, then they will be soluble. And same thing is true for both polar and non-polar. If I ask you why, so suppose the solvent is polar and the interaction there is due to dipole-dipole, and the solvent is polar and the interaction also is polar-polar. Now, if you dissolve both of them, to keep them constitute together, there should be a polar-polar interaction in both of them. Okay? Or else they won't be soluble. So this is the very thin line, and you would say that to define it, it's very difficult. So say for sugar, you would think that, okay, it must be a non-polar one, but it is a polar one. Whereas the benzene and anthracene, which are looking non-polar, and they are also not soluble in the water. Now, the next term is dissolution. What is dissolution? It is defined for a solid solute added to the solvent. When some solute dissolves and its concentration increases in solution. So the breaking down of the solid solute in the solvent is termed as dissolution basically. Then what is crystallization? So crystallization can be seen as the reverse of dissolution, where your solid solute particle crystallizes out of the solvent and gains the solid form. But a stage is reached when these two processes occur at the same rate. And in this condition, the number of solute particles going into solution will be equal to the solute particle separating out. And the stage is termed as dynamic equilibrium. So what is dynamic equilibrium? The rate of forward and backward reaction, where the reaction is a physical process, the dissolution and crystallization of any solid in solvent. And if they are occurring at the same rate, you will say that a dynamic equilibrium is reached. So here is a equation describing this dynamic equilibrium. You can see that the solute and the solvent are being constituted as the solution and they are reversing back to the initial form also. The solution which is not capable of dissolving any solute further at a given temperature and pressure is called saturated solution. So why it is written that at a given pressure and temperature? Suppose at 100 degrees Celsius, 5 gram of sugar is dissolvable in 100 milliliter of water. So this is just an example. Now, if you increase the temperature, this 5 gram amount will be increased and it is very, very definite. Okay. So you can take a fair temperature like 40 degree or 50 degree because after 100 degree your water gets converted into steam. So from 40 degree to 50 degree, if you increase, the solubility will also increase. So for a solution to be defined as saturated, you also need to define the temperature and the pressure. Now, what is unsaturated solution? Very simple. A solution which is capable of dissolving more and more solute into it are termed as unsaturated solution. So, a solution which is in dynamic equilibrium, which undissolved solute is the saturated solution. So, the example that we have taken here is an example of saturated solution because it has reached its solubility point. Okay. And it contains the maximum amount of solute dissolved in a given amount of solvent. And in this case, the concentration of solute is called as solubility. We have defined it already. What is solubility? It is the maximum amount of solute that is given and can be dissolved in a solvent. And it should be given at a definite temperature and pressure. Clear? So you can also define solubility in another way. So it is the concentration of the solute in a saturated solution. As simple as that. Now I have mentioned multiple times that you have to define or you have to fix the temperature and pressure. We will see why. Because the change in solubility is very obvious due to change in temperature. And it is different for different type of solution. Different for solid solution, different for liquid solution. Okay, so we will see them. Now, the solubility of a solid in liquid, like the sugar in the water, is significantly affected by the temperature change. How it is affected? We will study that with the help of a equilibrium reaction. Suppose this is your equilibrium reaction. Now, since it is a dynamic equilibrium, it means that the Le-Chatelier principle will be applicable. So, if it is an endothermic process, then on increasing the temperature, the solubility should increase. So, when the system or the process is endothermic, means it is absorbing heat of the environment. Now, if you apply more and more heat, then to attain the equilibrium back, this reaction will move in the forward direction to absorb that extra heat. So we can say it very clearly that your solubility will increase with increase in the temperature for endothermic process. But if it was exothermic, the solubility should decrease, and it is a direct application of the Le-Chatterjee principle. Coming on to the next factor, which is effect of pressure. So in case of the solution where we are dissolving a solid in a liquid, pressure has a very less role to play. And the reason behind it is that solid and liquid are not compressible, means they cannot be affected by the application of pressure. So it is written here, solids and liquids are highly incompressible, means they are practically unaffected by the change in pressure. But in case of gases dissolved in liquid water, this thing is not true, because we know it very well that gases are compressible in nature. Like your oxygen dissolved in a water up to a small extent is very valuable for the aquatic life present in it, which is feeding on that oxygen. So the dissolved oxygen is the cause for the sustenance of this aquatic life. But the solubility of gas increases with increase of pressure. So if you are applying more and more pressure onto the liquid surface, then you will be able to dissolve more and more solid particles which are gaseous in nature in the solvent. And it is very obvious, as you have seen its application in the soft drinks, where it is filled with CO2 at high pressure to keep it in the solution. The CO2 is trapped in the solution with this application of high pressure. And if you remove the lid, then you will see that due to removal of the lid, the pressure decreases and the amount of CO2 that was initially dissolved decreases. So, for a solution of gas in a solvent, we can consider a system. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume that this system to be in a state of dynamic equilibrium. Now, if you increase the pressure over the solution phase by phase by compressing the gas to a smaller volume, then the amount of gaseous molecules present above the liquid increases. And it will result in more gaseous particle going into that unit volume. And they will strike the surface of the solution at a much greater rate due to the application of pressure. And now they can be undergone into the liquid. So we can say that with the application of pressure, the solubility increases and it goes to a new solubility concentration. And this is our Henry law. Our Henry law says something similar to it, which is that pressure is directly proportional to the concentration of gas in the solution. Now, if I state the whole law, it is saying that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the surface of liquid or solution. Now, in place of concentration, we can use the mole fraction, because mole fraction is also a way to represent the concentration, and it is more good for gases to be represented in the form of mole fraction. So, we can now formulate the Henry's law once again and say that the partial pressure of the gas in vapor pressure P is proportional to the mole fraction of the gas chi in the solution. And this can be expressed as this equation, P is equals to KH chi, where KH is your Henry constant. Now, if we draw a graph, then what would be the plot? According to this equation, the pressure will be directly proportional to the chi. So it will give you a linear type of plot. This kH value or a Henry constant is defined differently for different gases, and it is a function of nature of the gas simply. So here is your kH value for different gases. You don't need to learn it, but what you can see here is that if you are increasing the gas molecular mass, then you are decreasing the kH value. For lighter gases, the kH value is very high. Like for helium, it is 144, and for heavier gases like vinyl chloride, it is 0.611. So you can easily see a decline with increase in the molecular mass. And it is also defined at different temperature. So at a higher temperature, you will see that the value of kH is increasing. Got it? Now, we can say from the Henry equation that P is equals to kH chi. So, kH is inversely proportional to the mole fraction. You can just rearrange it and get that thing. So, if you have a higher value of kH, then you have a lower concentration. Now, you can say it very easily that the gases with a higher molecular mass has a lower kH, that means your Henry constant, and greater solubility. Whereas, at a higher temperature, the solubility decreases as the value of kH is increasing. So, kH value for N2 and O2, they both increases with increasing temperature, suggesting that your solubility will decrease as a result in higher kinetic energy of the gases. We will see it. So, it is the reason why your aquatic life is more sustainable in a lower temperature as compared to the higher temperature, because on increasing the temperature, the solubility of oxygen decreases and aquatic life finds it difficult to breathe. Now moving on to a question. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar. So this is the pressure, and kH value is also given 76.48 kilobar. Remember, we have to look for the unit because one has a unit of bar and one has a unit of kilobar. So let's see. You have to calculate the number of millimoles that is dissolved in 1 liter of water. So first of all, we know that the mole fraction of a given gas is related to the partial pressure as follows, which is according to Henry's law. Chi is equals to P by KH. So it is just a rearrangement of the equation. P is equals to KH chi. So pressure was given 0.987 bar, and we have converted this 76.48 kilobar into bar by multiplying it by 1000. If you do this calculation, you will get your value as 1.29 into 10 to the power minus 5. But you have to decide that what is the number of millimoles of N2 dissolved in 1 liter of water. So we can say it directly that 1 liter of water would contain 55.5 mole, because the density of water is taken as 1. So that will give you 1 gram of water present in 1 liter of water. And in 1 gram, how many millimoles will be there? How many moles will be there? So you can just calculate it. It's very easy. So if N represents the number of moles of N2 in solution, then we can say that N mole of what? The solute by N mole plus 55.5 mole of water is equals to 1.29 into 10 to the power minus 5, which is our mole fraction. Then, since the solubility of nitrogen is very less, we can neglect its mole in comparison to 55.55. Thus, we can write n is equals to 1.29 into 10 to the power minus 5 into 55.5. That will give you 7.64 into 10 to the power minus 5 moles. So this is your number of moles. Remember that 1 liter of water has 55.5 moles. So this is a calculation from the density of water, which is equals to 1. So the density of water is 1 gram per milliliter. From there, we have got this value. Now, if you convert this moles into millimoles, you will get 0.76716 millimoles. Let's multiply this thing by 10 to the power minus 10 to the power 3. Okay, to get the millimole. Then what are the applications of Henry law? First is the solubility of CO2 is increased in the soft drinks. We have already discussed it earlier. Then scuba divers are finding it very difficult to sustain with this high concentration of dissolved gases at high pressure inside the seas. So what did they do? They dissolved the nitrogen to avoid this. So scuba divers, to cope with this high concentration of dissolved gases while breathing in air at high pressure at underwater, use this Henry law to avoid that situation. So what is happening? When the pressure is increasing, the solubility of atmospheric gases increases in the blood. But when the divers come out of the sea, the pressure decreases all of a sudden, and this results in release of the extra amount of gas dissolved in the bloodstream. Therefore, resulting in the formation of bubbles of nitrogen in the blood. Now, this thing is very painful. To avoid such bends and to avoid the high concentrations toxic effect of nitrogen, the tank they are using contains the diluted helium. They contain air with diluted helium, where we have 11.7% helium and 56.2% nitrogen and 32.1% oxygen. Now, a very good question comes here. Why they are inserting helium only? Because we have seen earlier that the value of KH was very high for helium as it is a lighter gas. So, due to this, its solubility is very less as compared to nitrogen and oxygen. So, on increasing the pressure, it won't go that much into the bloodstream and cause bends. So, for that reason, we are filling it with the helium. Similarly, there is a difficulty at high altitudes also, where the pressure decreases and the amount of oxygen present in the blood decreases, resulting in a very hectic situation. So, the climber feels nausea and even vomits due to this less amount of oxygen reaching their brain, and they become weak and they are incapable of thinking properly. This situation is called anoxia. Now, talking about the effect of temperature on the solubility of a gas in a liquid. So, we have already seen and is justified experimentally that your KH value is increasing on increasing the temperature. So, that would result in a decrease in solubility. So, this thing is mentioned here that your solubility decreases with increase in temperature. The reason behind it, it's very obvious. Now, your gaseous molecule at a high temperature has enough kinetic energy to escape the intermolecular force and go into the atmosphere. So, when dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to condensation, and heat is involved in this process. Now, you have already seen what is dissolution. Dissolution process involves dynamic equilibrium, and it follows the Le-Chatelier principle. And as your dissolution is an exothermic cases for the gases dissolved in liquids, the solubility decreases with increase of temperature. So, this is the reason behind the less solubility at higher temperature. Then we have a question here. H2S, which is a toxic gas and has a rotten egg-like smell. So it is used for the qualitative analysis. But if the solubility of H2S at STP is 0.195 molar, then calculate the Henry constant. How will we do it? So it is already given that 0.195 is the molality. That means 0.195 moles of H2S is dissolved in 1000 grams of water. So this is the definition of molality, number of moles per kg of solvent, and per kg means 1000 gram. So moles of water can be calculated from here, in which this 0.195 mole of H2S is dissolved. 1000 by 18, that would give you 55.56. So you can just go back and see that this was the amount that was present in 1 liter of water. Now, what is the mole fraction of H2S? We already have the moles of H2S and water, so we can put it in the equation of mole fraction. Putting this will give you 0.0035. Now, if you do this calculation, at STP, the pressure is 0.987 bar. According to Henry's law, we can say that P is equals to KH chi. We have the pressure already. Chi is being calculated. So KH can be written as P by chi. So P by chi will give you 282 bar. Remember, KH has a unit similar to the pressure because mole fraction has no unit. Then our next question. The Henry's law constant for CO2 gas is 1.67 into 10 to the power 8. Then we have to calculate the quantity of CO2 in 500 ml of soda. Water when packed under 2.5 CO2 pressure at 298 Kelvin. So what is being given here? Your Henry law constant is given here. We have to calculate the CO2 which is present in 500 ml of water. The pressure is also mentioned. First, we will calculate the what? We will calculate the mole fraction. So it is given that KH is this. So pressure will be equals to how much? So to convert the ATM into Pascal, we will multiply it by 1.01325. So they are almost equal. There is a very slight difference. Multiplied by 10 to the power 5. So this factor is extra. That will give you 2.5 into 10 to the power 5. So you can see there is no major difference in the significant terms. Now, according to Henry's law, we can put it here. Further, we can write chi is equals to pressure of CO2 by KH. So if you put the values back here we have calculated the pressure of CO2 and we have the value of KH already. It will give you 0.00152. Now, chi can be written as the number of moles of CO2 by total number of moles. Since your amount of CO2 is very less, we can neglect that CO2 and write the equation as number of moles of CO2 by number of moles of water. Then we have this value. Yes, we have this value. We have the chi. And we have the ml of what? Ml of soda. So since your CO2 is not that much as compared to NH2O, we have already ignored it. So in 500 ml of water, the volume of water would be 500 ml. Okay, because the amount of CO2 is very less, so there will be very less change in the volume due to adsorption of the CO2 gas. So neglecting the amount of soda present, we can write 500 ml of water will have 5000 gram of water. So this is directly from your density. So density must be 1 gram per ml. So we are getting this thing. Now 500 means how many moles? Divide this thing by 18. That will give you 27.78 moles of water. So we have the moles of water, we have the chi. Now we can get the number of moles of CO2. If you put this thing here, you will get moles of CO2 as 0.042. Now, to calculate the mass, we will multiply the CO2 mass with the number of mole. This will give you 1.848 grams of CO2. So this was all for today's class. Thank you for attending the lecture.